hypersurfaces. First of all, I would like to thank organizers for giving me this opportunity to talk here. Yeah, this is joint work with Kim and Wong. Yes, so let me begin with the background of this talk. So, okay, let me be very quick or brief about K-stability. So the important features of K-stability or K-stability is relation, conjectural relation for Q-Fano varieties. The relation or conjectural equivalence between K-stability and K-polystability and the existence of Kähler-Einstein metric. Of course, this relation is equivalence for smooth case. And one more features is that it is very important in the moduli theory of Fano varieties, which are called K-moduli. And also, I do not make use of its definition I put here. This is not the original definition, but so for Q-Fano variety X, it is K-stable if and only if this beta of E is positive for any prime divisor E over X, where beta is the log discrepancy minus these guys. And this is the volume of the anticanonical divisor subtracted by E. Okay. So let me go to birational super rigidity. For Fano variety, when I remove Q, it means that Fano variety has terminal singularity. So for Fano variety of Picard number 1, birational rigidity or superrigidity means uniqueness of modifiable space structure in the birational equivalence class. So it implies non-rationality in a strong sense. So this notion plays an important role in birational geometry and especially rationality problem. So here is the precise definition. So let X be a Fano variety of Picard number 1. Then it is birationally rigid if for any modifiable space y over t, such that y is birational to x, one always has isomorphism between x and y. So y is of course Fano variety of Picard number 1, and it is isomorphic to x. So this is a uniqueness of the modifiable space structure. So we say that X is birationally super rigid if it is birationally rigid and the group of birational automorphism coincides with biregular ones. So every birational self-map is biregular. This is slightly stronger than rigidity, of course. So I will talk about more. I will talk about the examples later. So before that, I talk about alpha invariant and K-stability. So let's go back to K stability. Let X be a Q-Fano variety of dimension n. Q-Fano means it as KLT singularities. So the alpha invariant of X is defined as the sup of this lambda. Uh, so where, sorry, X lambda D, the pair X lambda D is log canonical for any effective Q divisor D, which is Q linearly equivalent to minus K. Yes, this is called the alpha invariant. And yeah, roughly speaking, this alpha measures the singularities of the anticanonical Q divisors. And so alpha X is, if the alpha X is bigger, then the singularities are milder. So here we have some theorem, famous theorem by Tian or Odaka Sano. If alpha invariant is not small, to be precise, greater than n over n plus 1, where n is a dimension of X, then X is K-stable. So yes, we have this kind of criterion. So again, roughly speaking, mildness of singularities of anticanonical Q divisors implies K stability. Then again, so we go to birational superrigidity again. So we have a criterion or characterization of birational superrigidity. Let X be a Fano variety of Picard number 1. Then it is birationally superrigid if and only if for any mobile linear system M on X, this pair is canonical. Where M is a positive rational number such that M is defined by this relation. Okay, so birational superrigidity is equivalent to mildness. In this case, not log canonicity, but the canonicity of singularities of anticanonical Q linear systems. Here we have systems, not divisor. And so on the other hand, we have this relation, mildness. Here, I mean this relation, mildness of singularities of anticanonical Q divisors implies K stability. So we may expect this relation or implication. So yes, here we have conjecture. So conjecture says that any birationally superrigid Fano variety is K-stable. So yeah, of course, the converse is not true at all. So there are many K-stable Fano varieties which are not birationally superrigid. And birational superrigidity is a very strong property. So we may expect this conjecture to hold. Yeah, and so I explained some results, some partial results. So for birationally super rigid smooth Fano variety of index Fano index one, if the anticanonical linear system is base point free, then x or precisely the pair x minus k is slope stable. So here I don't explain the definition of slope stability, but it is a similar notion of k stability, and it is weaker than k stability. Similar but weaker than k stability. So this is a very partial result. Yes. And we need many additional assumption. We need smoothness, and index is one, and base point freeness of this system. Recently, we have one more partial results which supports this conjecture. So this is proved by Stibitz and Joonyeong. It says that for a birationally superrigid Fano variety, so it is not necessarily smooth. It can be, terminal singularity. So alpha, if alpha is at least 1/2, then it is K stable. Yes, this is so far. This is the most strong evidence for this conjecture. Yes, I explain examples or known results for K stability or birational superrigidity of Fano three-folds, Fano varieties of Picard number one. Okay, first I will talk about smooth Fano three-folds of Picard number one. So because I will talk about birational superrigidity, I always consider Fanos with Picard number one. So they are okay. Birationally superrigid smooth Fano three-folds are determined, classified. There are two deformation families. One is smooth chaotic three-folds. And this is famous result by Iskowski-Manin. And these are K-stable by Kento Fujita. And another one is sextic double solids, which are degree 6 hypersurface in this weighted projective force space. Or in other words, it is double cover of P3 branched along degree 6 hypersurface. Yes, its birational superrigidity is proved by Iskowski. And these are also known to be K-stable by Chertov Pak Won. Okay, next I talk about hypersurfaces. So let XD be a smooth hypersurface in Pn plus 1 of degree D, defined by degree D equation. And here I assume n is at least 3. then this xd is birationally super rigid if and only if d is equal to n plus 1. I mean, which is equivalent to saying the Fano index is 1. Okay, this is proved by Iskovsky-Manning for threefold case, and Pukurikov, and finally by Dufresne. And for birationally super rigid ones, namely degree n plus 1 case, x n plus 1 is always case stable by Kento Fujita. Yes, so summary is this conjecture is true for smooth Fano threefolds and the smooth hypersurfaces. Okay, so let's go to the weighted hypersurfaces. So let's consider further examples of Fano threefolds. K-size smooth Fano threefold weighted hypersurface is hypersurface in weighted projective force space. Here we have X. It is a hypersurface in this weighted projective space, where this subscript D is the degree of the defining equation of X, such that X is K-size smooth, meaning that affine cone is smooth outside the origin of the affine 5 space. And X, so by the K-size smoothness assumptions, X automatically has only cyclic quotient singularities. And we require here that X has only terminal singularities. So terminal cyclic quotient singularities. And the sum of the weights minus D is positive. So which I denote by iota X. And this means that minus kx is ample. So X is Fano. So this iota is called the Fano index of X. Okay, here we have classification of these objects. So there are 95 families of K-size smooth Fano threefolds, Fano threefold weighted hypersurfaces of index 1. We have 95 families. And we have 35 families for index at least 2. Yes, then I explained birational non-results on birational rigidity and case stability. So it is proved by Kurikov-Reed for under the generality assumptions, and later Chertov-Pak removed the generality assumptions, and it is proved that any K-size smooth Fano threefold weighted hypersurface of index 1 is birationally rigid. And to be more precise, among the 95 families. There are two kinds of families. One is called birationally superrigid family. That consists of 50 families, and whose this family consists whose any member, any KSI smooth member is birationally superrigid. And another one is called birationally rigid family, whose general members are strictly birationally rigid. I mean, birationally rigid and not superrigid. And some special but KSI smooth special members are birationally superrigid. So all of them are birationally rigid, but we have two kinds of families. Any member is superrigid, or general members is rigid. And yeah, important thing is that inside this family we have superrigid members. Okay, so theorem. It is okay. It is proved by Chertsov that general KSI smooth Fano threefold weighted hypersurface of index one is K-stable and admits a Kähler-Einstein metric. So general means that general in the given family. Yes, so we have K stability for general these objects. So now I state main results, and so basically we would like to check conjecture for these objects for weighted hypersurfaces. Yes, so our main theorem is as follows. For KSI smooth Fano threefold weighted hypersurface of index one, its alpha invariant is at least one half, at least half. So yeah, we don't need any generality assumption here. So together with the result of Stibitz Juan, we have the following. Birationally superrigid KSI smooth Fano threefold weighted hypersurface. Oh, yes, maybe I should put index one here, but is K-stable. Yeah, I should put index one here, but let me explain from now on. So by the very recent results, for KSI smooth Fano threefold weighted hypersurface, X of any index, if it is birationally, for KSI smooth Fano threefold weighted hypersurface, it is birationally rigid if and only if its index, Fano index is one. So if X is birationally rigid, then its index is automatically one. Thus, we can say as follows: the conjecture is true for KSI smooth weighted hypersurfaces. Yes. Okay, so in a week ago, we upload this result into archive, and after that, we have a suggestion from Chen Shu and Zhang. They say that one can generalize the result of Stivitz's Zhang as follows. And yes, for a birationally superrigid Fano variety X, so this inequality implies X is uniformly k-stable. I don't give a definition here, but this is a priori stronger notion than k-stability, than ordinary k-stability. So their suggestion is this implication. So combining another known results, another very strong known results by Lee Tian-Wan, uniform k-stability implies k-stability and existence of K-Einstein metric. So we can conclude the existence of K-Einstein metric for birationally superrigid weighted hypersurfaces, Fano threefold weighted hypersurfaces. Yes. Okay, is there any questions so far? Okay. So one thing I should mention here is that our main theorem says, yeah, we prove this inequality for any k-size smooth Fano threefold weighted hypersurfaces of index one, but we can only conclude k-stability only for birationally superrigid ones. So for birationally strictly rigid ones, we cannot conclude k-stability.
Takuzo, I have small question.
Yeah.
Do you really have a case when alpha equals 1/2?
I
No.
don't think so. But yeah, we can only prove. We cannot remove equality case.
I see.
But I believe there is no such example. Thank you. Yes. Okay. So I'm explain a very rough sketch or proof. So let X be a k-size smooth Fano threefold weighted hypersurface of index one. And the goal is to show that alpha px is at least half for any point p. So where alpha p is the local alpha invariant defined as the infimum of log-canonical threshold, where d runs over effective Q divisors, linearly equivalent to minus k. And yes, this the global alpha is the infimum of this local alpha invariant. So actually, we need hundreds or thousands of computations for these invariants. So let me explain the most typical method for computing or bounding alpha p for smooth points. So let p be a smooth point. And so step one is to find an effective divisor S on X vanishing at P to high multiplicity. And okay, next show that its log-canonical threshold is at least half. So where A is such that A is defined by this relation. And yes, for our purpose, we need to show this kind of inequality for any Q divide, effective Q divisors. So we pick up some singular S, and first of all, we check this inequality. And then next, find the linear system H on X such that its base locus is a finite set of points containing the point P. So then we can choose a general member T so that, okay. First of all, I have to take divisor D. So I pick divisor D, and yeah. And then we pick a general T so that this set is a finite set of points, meaning that these three divisors intersect properly. So next, so let B be the positive integer defined by this one. Then this local intersection number at P is at least the this one, the product of multiplicities. And it is, of course, less than or equal to this global intersection number. And here we have this one. So from this, we have inequalities for the log canonical thresholds. This inequality is a general one. We always have this inequality. And here, by this inequality, we have the second one. So this gives a lower bound. So there's a final step. We are done if this value is at least half. So we need to pick up S and this linear system satisfying this inequality. So this is a most typical method of bounding log canonical threshold or local alpha invariant. So next, so for singular points, we need several distinct methods of proving this inequality. So I pick up one of them and let me state it without proof. So let P be a terminal quotient singular point on Fano threefold. This is a general lemma, Fano threefold. And let phi be the Kawamata blow-up at P. It is a weighted blow-up. Yeah, it is a particular weighted blow-up. Then suppose the one cycle, the self-intersection of minus ky is not in the interlinear of the cone of effective curves on y. And suppose that there exists a prime divisor S on X whose proper transform on Y, S tilde, is linearly equivalent to minus mk y for some positive m. Then alpha, local alpha invariant is at least one. So for many singular points of our objects, k-size smooth Fano threefold weighted hypersurfaces of index 1, these two assumptions are verified in the proof of birational rigidity, which are done by Chertoff-Park. So we have this inequality for many singular points. So let me explain the alpha invariance for another singular points. This is the most difficult, complicated or difficult involved case. So here X is again k-size smooth weighted hypersurfaces of index 1. So its singular point P is called QI center. It is quadratic involution center. If by a suitable change of coordinates, we can assume P is this point. So the coordinates I denote x0, x1, x2, x3, and w for the homogeneous coordinates, and w has weight a4. Okay, and here we do not assume this kind of thing. Okay, and the equation of x is of the form. This is the quadratic with respect to the variable w. The equation is of the form. So if P is a QI center, then there exists a birational involution sigma of sigma P that factorizes as follows. Here sigma is here, and first we have projection to this first four coordinates, this threefold projection, and it is clearly generically 2 to 1 because it is w quadratic 2 to 1. So we have birational involution interchanging these fibers. This is sigma p, and it factorizes in this form. So let x be a Kawamata blow-up or weighted blow-up of these weights at the point P. And here phi is the same Kawamata blow-up. And that here we have flop. So this is so-called circuits of link. Anyway, we have birational involution. And for QI center P, this sigma is biregular if and only if the polynomial G is divisible by x0. Here, G is divisible by x0. And we say P is degenerate in this case. So, okay, so the presence of this kind of involution it breaks superrigidity. So if, yeah. So, okay, so we have this result for degenerate QI center P, which is a cyclic quotient singularity of this type. And its alpha, local alpha invariant is equals A4 plus 1 over 2A4 plus 1. And it is computed by the LCT of H where h is this divisor. So in the case of a0 is 1, so degree of x0 is 1. Otherwise, the alpha invariant is 1. So anyway, we have, yeah, this number is at greater than half. Yeah, we have this proportion. And so, okay, let's see one example. So consider degree 21 hypersurface inside this space. And its equation can be written in this form, in this way. The singularity of this x is 1 point. 1 point is this point, and it is of type this one, and it is QI center. Yes. So we can prove alpha p is at least half for smooth point p. I mean, point other than this singular point. And we, in the general case, I mean non-degenerate case, this alpha invariant is, we only have inequality for this singular point of general case. And in this degenerate case, we have equality by the previous proposition. So anyway, we can prove the desired inequality. And in addition, if X is birationally superrigid, in this case, it is equivalent to saying that this singular point is degenerate. If superrigid, then we have these inequalities. So our expectation is that alpha, global alpha is equal to this one. But this is, I think the smallest example for alpha invariant for weighted hypersurfaces. Of course, birationally superrigid case. Okay, so this is a very rough sketch of proof, the idea of proof. And finally, okay, is there any question so far? Okay, so next, this is a final section, and consider question about on lower bound of alpha invariance. So the question is alpha is always satisfies this inequality for any birationally superrigid Fano variety of any dimension, arbitrary dimension. So this is my question. And also, if yes, then we can ask more. Can we expect a better lower bound? Better one. These are questions. I think this is natural question because if this is automatically satisfied, then the conjecture is follows. So okay, I don't have any answer, but I show you one example. So let A be a integer, at least 2. And consider a k-size smooth weighted hypersurface of degree 2a plus 1 inside this space. This is a plus 2 dimensional weighted projective space. And in general, equation is can be written down in this form. It is quadratic with respect to w. W is the coordinate of weight A. And so in this case, if we choose F and G general, then X is a Fano variety of Picard number 1 and index 1. And dimension is A plus 1. And it has unique singular point P, which is of type this one, and this is terminal. So yes. And when A is 2, this is a threefold of index 1. So this is an object of our main theorem. And yeah, these are birationally rigid, and it satisfies this inequality. Yeah, and we consider a more higher dimensional cases. So similarly to the threefold case, we have birational involution again because it is quadratic. Birational involution, and it is biregular if and only if G is divisible by x0, the same situation as before. So in this case, we say X is degenerate. So our expectation is that if X is degenerate, then it is birationally superrigid. So this is true for A equal 2. I mean, threefold case by the result of Chertsov-Park. And but it is widely open for higher dimensional cases for A at least 3. Okay. And next, one can show, as in the case of as in the threefold case, one can show that in the degenerate case, we have this equality. This local alpha is equal to A plus 1 over 2A plus 1. It is, of course, greater than half, but this equality implies that global one is at least this local one. So we have this inequality. And as A goes to infinity, yeah, this of course goes to half. And so if our expectation is true, then we have birationally superrigid Fano variety whose alpha is arbitrarily close to half, or possibly smaller than half. So So, okay, for this second question, we cannot expect a beta bound. So half is optimal. If this question is yes at all, then this number is optimal. So yes, I stop here. Thank you very much.
Thank you, Takuzo.
Thank you.
Any questions?
I have small question. So if in birationally superrigid case, quite often I think it's probably very often, I don't remember, your threefold has an involution.
Yeah.
So
super rigid case?
Yeah, in many superrigid cases, this threefolds has natural involution because equation.
But you mean biregular involution?
Biregular involution.
Yeah, I see.
Yeah, then one can probably use the fact that G equivariant case stability coincide with just G K polystability and something like this. Yeah, and then I think in many cases it basically reduce computation of some centers. You can to the fixed point of the involution. So basically means you need to consider only points on the surface, fixed point on the surface. Yeah, so it may help a bit.
Yeah.
So just a bit. But it's just a remark.
Yeah, thank you. I think so. I agree. Yeah.
Okay. Any others?
Did you try to compute delta?
Not yet. But I feel it's for me it's too difficult.
Maybe after pandemic we should meet somewhere in Hokkaido.
Yeah, I hope so. Hokkaido, yeah.
To work on this problem. Yeah. Okay.
Okay. Thanks a lot then.
Thank you.
Thank you, Takuza.
Thank you. Yeah.
Long time no see.
Yeah.
Sorry, I was a bit late. Yeah.
So you had a class.
Yeah. 1/3 of students wants to have real class. So
I see.
I volunteered.
I see.
Some people said they're not going to do this.
Yeah.
But it's okay. Hi, Jihun. How are you?
Hi, how are you?
Good. Oh. Yeah. Good. Long time no see as well. Good.
Long time no see.